Hi, this is going to be a video for my stat class, mainly the lecture class as we are in the online environment right now. And this is for chapter 10 is mainly what we have now. So we're at our last chapter, which is hard to believe that this is the last one, but I wanted to have, or I have just a few quick announcements to kind of go over here. So I'm recording this on Saturday, the 25th, so we're almost in week 15. It'll start tomorrow. So of course, remember, we only have 16 weeks of the semester. So this week, you should be finishing up your last unit, so unit 5, which is chapter 9 and 10, and then preparing for the final, right? So next week, or week 16. So tomorrow starts week 15, and then next Sunday we would start week 16, and then that ends May 8th. And so all the due dates are extended until that day, May 8th. So you can work on anything, chapter 1 through 10, until that date. The final exam actually is ready now in my math lab if you want to do it, but you can only do it once. So make sure you're ready to take it. When you do take it, you have 2 hours to complete it, and I think it was like 30 questions. It's comprehensive for my lecture class people. So there's, we've got 10 chapters, so there's 2 or 3 questions from every chapter, basically. There's a practice final exam on my labs, but I'm also going to send out a paper version of what we would have reviewed in class. And that is what we can discuss some on our Microsoft Teams meetings. So I'm going to schedule those for next week, Monday at 7 p.m., Tuesday at noon, and then Thursday at 10:30 a.m. If none of those times work for you, I tried to kind of do them different days, different times. But if you need a different time, or if maybe we need to have a weekend one next weekend, next Saturday or Sunday, we can add that on too. It just kind of depends on how much interest I have for them. But I'll stay on those for at least an hour. But, if we have a lot of conversation, it may last a little longer. But if you can't be there right at the beginning, just join whenever. And so I'll send you the links to join on to those. Microsoft Teams, if you've never used it before, it's pretty easy to use. You don't have to have your computer or an app to do it. You can just call in and listen, to what we're talking about. But if you want to see like the screens that I'm sharing and all that, then of course you would need to use your computer or the app or whatever for that. So I talked about last time that I need to upgrade your grade books or update your grade books. And I decided that probably the easiest way to do that was just to go and put all your Blackboard grades into my labs. And so that way it is automatically updating as you're working through your different assignments, especially now that, 2 of our tests have been in my labs and your final will be in there and all that. So I've gotten partially done. I know at this point I have 1 class finished. My Monday, Wednesday class is finished. By the time you watch this, they may all be finished, but basically you'll start to see all your grades from Blackboard in MyLabs. So when you look at your MyLabs grade, that would be your actual overall class grade. Now, the only thing you have to be careful of in my math lab is if there are assignments that you haven't even started, like let's say you don't do any of chapter 7 or 8 homework, but you do the test and, then you finish unit 5 and then you finish your final. Well, it's going to show your overall average, but it's not going to factor in the zeros that you will get for those chapter 7 and 8 homeworks. Now, if you've started them and you got 1 question right, then that is factoring into your grade. But if you haven't even opened a certain assignment, then those zeros may not be counting towards your overall average. So be kind of careful, when you're looking at your overall grade. Think about, if you have completed everything or not. And then, like I mentioned last time, please complete the course evaluation in Blackboard. It's supposed to close, I think, on May 1st. So if you could get that done, I would really appreciate it. I can't really see who's done it and who hasn't. So you may have all completed it already, so you're tired of hearing me say it. But if you could do that, I would be very grateful. All right, so today, Chapter 10 is what we're going to be working on. And Chapter 10, let me see, let me make this a little better here. Okay, so Chapter 10, we're talking about hypothesis testing. I said Chapter 9 and 10 are similar. Both of them are ways we're going to figure out how to tell if this statistic is really unusual or not. And we've been doing that throughout the semester using different methods. So we may have started out back in Chapter 3 using our z-score or using the empirical rule to kind of see where our statistic fell and determine if that was unusual or not, right? In Chapter 5 and 6, we talked about probability. So we started to think about if something has a less than 5% chance of happening, then that's pretty unusual, right? And so that's also a way we could determine something as being an outlier or an unlikely event. And then in Chapters 7 and 8, we started to kind of put those two concepts together and look at, all right, I've got this normal distribution. I've got a value that fell in a certain place. Now let me calculate the probability of that happening, right? And through those two chapters, we also kind of talked about if it was a less than 5% chance of happening, then that was pretty unlikely. If something had a 23% chance of happening, well, of course, it's not going to happen all the time, right? But it's not that unusual, right, if it did happen. So it'd be like a 1 out of 4 chance or something, right, of happening. So in Chapter 9, we use confidence intervals, right? And confidence intervals are going to help us determine if something is unusual by either comparing two intervals. So like if you have two different studies and you're trying to tell if one of them really shows an increase versus another one. When you compare them, you would use the margin of error with the statistics and look at the intervals, right? And if the intervals overlap like this, then they're not statistically different, right? Because they still have some common outcomes in the middle here, right? But if they're totally separate like this, then you would say, okay, one of these studies is completely different from the other one, right? It's either completely higher or completely lower, depending on which one, you're comparing. And so that was what we used in Chapter 9 to determine if something was unusual, right? Or if there had been a significant change. Now in Chapter 10, we're thinking of another way to do this inferential statistics using hypothesis testing. And so with hypothesis tests, there's a lot of startup work that you have to think about, because the hypothesis test is more structured in that you're starting out by saying, this is what I'm going to test. And then you collect the data and you show what your results are. You compare to what would be considered an unusual result. And then you decide if you're going to reject or fail to reject your hypothesis. So this is what we would see in studies. When we looked at some of those clinical trials or different studies that we've looked at throughout the semester, if we looked at the actual study that was printed in whatever journal it was, we would have usually seen some sort of hypothesis laid out. We might see a confidence interval or we might see a p-value. And so both of those are related to these last two chapters. So this is kind of how you would actually complete your statistical test. So again, remember, this is just kind of a quick overview. I say quick, but I guess it may not be super quick, but it's going to be quicker than I guess what the actual lecture video would be. So if you haven't watched those, be sure you watch those on YouTube. All right, so the first thing we're going to do in hypothesis testing is start by stating the hypothesis. So what are we testing and what are we trying to prove? So we have two hypotheses. The first one here, this is called the null hypothesis. So it's H sub 0, so you've got a little 0 kind of down here. So that's what we're starting with. This is what we're true. So we're assuming that some percentage of people do this, or we're assuming that the average weight of newborns is this, right? So we're assuming something is true, and often this may have come from a prior study that we're wanting to compare to, or maybe it's just some kind of common knowledge. That's like, we assume normal human body temperature is 98.6. So maybe you're trying to see, is that really true or not? So you would start out with, I'm assuming that the mean body temperature is 98.6, and then I'm going to collect data and see if I can prove otherwise, right? So the alternative is the H sub 1 here, and this is the hypothesis we want to prove is true. So we want to show that mean body temperature really is greater than 98.6, or we want to show that the percentage has decreased since last year, okay, something like that. So in the null hypothesis, you're always going to have an equal to sign. One of your two parameters, you're either going to have mu or you're going to have p, and that depends on, again, like we did in chapter 9, whether you're doing means or proportions. In the alternative, you're going to have that same parameter, mu or p, and then you're either going to use a less than, a greater than, or not equal to. And these values that they're equal to or not equal to are going to be the same values. So if I have mu equals 98.6 up here, I'm going to have mu greater than 98.6 down here, right? So I'm going to have the same number. The only thing that's going to change from one hypothesis to the next is whether we have a less than, greater than, or not equal to down here. And you should be able to figure that out based on what the problem is asking. If it says, has there been a decrease? Well, then we're using less than. If it says, have scores increased over the last year? Well, you're doing greater than. If it says, has there just been a difference or has something changed, then you would do a not equal to, okay? Because then you're actually concerned with less than or greater than. Okay, now if you look in the book, if you've looked through some of the material in the actual e-textbook, then there's actually two methods you can use. You can use the critical value method or you can use the p-value method. We're just going to talk about the p-value method because honestly it's the most commonly used, and so at this point, we can only retain so much information, right? So we're just going to get straight to the point. We're going to do the p-value method. It's also a little easier because that's what our calculator does. So that's why we're doing that, if you happen to look in the book and wonder why we're not doing the other method. But so using the p-value method, the p-value is the property of getting a statistic as or more extreme than the one we got if the null hypothesis is true. Now this technically is what we have already been doing. Let me see this up for you real. All right, so I opened up some notes that we did back for chapter 7. Doesn't really matter if you go back and look at specifically which one I'm talking about here. But this was one where we had a normal distribution. The mean was 20, standard deviation was 2, and we were wanting to know the probability of getting greater than 23. Now we could also be doing something like this with hypothesis testing. Now we would also probably be doing the sampling distribution when we're doing hypothesis tests, but let's just pretend this is a sampling distribution. We've already done all the conversions or whatever. But this here, this trying to calculate, that is going to be our p-value. Okay, so like when we calculate this and we get this 0.0668, that's a 6.68% chance that it'll take more than 23 hours. Okay, now it says the p-value is the probability of getting a statistic greater than or less than, or however you want to put that here. It just depends on what your alternative hypothesis is. As extreme as the one that we got. Okay, so here, if we got the statistic 23, what's the probability of getting something more extreme than that? Well, 0.0668, right? It's just that area to the right. If we wanted to know the probability of getting something less than that, then we would, do this area, and that would be our p-value. So the p-value is calculated based on what we think the true mean is of the distribution. So like in this one, we thought it was 20. That would be our null hypothesis. And so we're saying if our null hypothesis is that the mean is 20, what's the probability that I would get a sample mean of 23 or more? And so we've been calculating these p-values before. We just had a p-value, but we're really doing the same thing we've been doing, okay? It's just all kind of in one package now, combining all the stuff we've talked about over the last several chapters. All right, so the p-value is just that area. Now, in general, we would say that if that area is small, if it's a small area, then we would say it's an unusual statistic, right? We would say that's something that's not very likely to happen. So if that area or the p-value is small, we're going to say that the null hypothesis is not true. And the way we say that is that we're going to reject the null hypothesis and we're going to accept the alternative. So that's telling us there is evidence that the proportion or the mean has changed. This is a significant result, or it is an unusual result, or it's unlikely to have happened just by chance. So all those kind of mean the same thing, right? We could just say it in different ways. But if our p-value is small, we're going to reject the null and accept the alternative. If the p-value is large, so if something has a 20% chance of happening, well, that's not that unusual, right? So we would say, well, yes, we got somewhat of an extreme statistic, but it really wasn't that unusual. So we're going to fail to reject the null hypothesis, which just means we don't have enough evidence to say that the null hypothesis is not true. The null hypothesis may not be true, but we don't have the evidence to say that with our results. Okay, so the difference is probably just due to sampling error, because we talked about in Chapter 9 how we have sampling error in every sample, and so we have to deal with that, right? So we could also say this is not a significant result. It's not statistically significant. So then moving on, how do we determine if our p-value is large or small? So in the past, we said 5% was kind of the limit we looked at. But now we're going to define that a little more specifically, and we're comparing it to our alpha level, also called the significance level. And this is something that would be set at the beginning of the study. The most common one that you're going to see is 5%, but you could use 10%, or you could use 1%, or you could use something weird like 8%. But generally, most studies are going to use an alpha of 5%. If you're talking about something that maybe is more important, like maybe you're testing some sort of new medicine or something, and you want to be very sure that the result and the conclusion you make is correct, then you might use a smaller alpha level. You might say, okay, I have to get less than 1% probability for me to believe that this new drug is really better, right? And so if you can get a result that's that far away from the expected null hypothesis, then you're pretty confident, right, that you made the right decision. And so what alpha does is it controls the type 1 error. And type 1 error is when you reject the null hypothesis, but you shouldn't have, right? So we want to try to make sure that if we do go through all this trouble of doing the study and we get to the end and we say the null hypothesis is not true, we want to make sure that we're pretty confident at that point that we made the right conclusion. And so that's why our alpha levels are low, because that's saying this is the chance that you made a mistake, right? So if our alpha is 5%, that's not too bad, right? There's a 5% chance we were wrong, but there's a 95% chance we were right, So same thing with confidence intervals, right? Confidence intervals, 95% confidence, it's the same thing, right? I'm 95% sure of this interval, but there's always that 5% chance that, we just got one of those results that wasn't what we expected. All right, so we compare the p-value to alpha, and then that's what's going to tell us if it's large or small. So if the p-value is less than alpha, then it's small. Okay, so then we reject the null, accept the alternative. If the p-value is greater than alpha, then we would fail to reject the null, so that means it's big. In the calculator, we're going to use the one-prop test for proportions and the t-test for means, kind of just like we did for intervals. The only difference is now it says test instead of interval, right? That's going to give you your test statistic, which is either a z or a t, z for proportions, t for means, and it will also give you the p-value. So then all you'll have to do is kind of plug it in where it's needed. Let's look at these examples here that I have on the practice test. All right, so Canon says their ink cartridges should print an average of 1,062 pages, but Lexmark wants to prove that it's actually less than that. They take a sample of 70 printers with Canon ink cartridges and find the mean number of pages printed was 1,041. Using a sample standard deviation of 59, an alpha of 0.05 or 5%, right? Does Lexmark have enough evidence to say that Canon's claim is false? So some things you're looking for here to know if it's means or proportions. Same thing that you would look for in Chapter 8 with sampling distributions or Chapter 9 with confidence intervals. If it's means, you will have a standard deviation and it'll talk about averages usually. If it's proportions, often it's talking about a study or a poll. There's no standard deviation given, and they usually mention percentages or proportions, right? So in this one, I kind of underlined some of the important words, right? It says an average of 1,062 pages, the mean number of pages. We do have a standard deviation here, right? So that tells me that we're doing means. So if we're doing means, then we want to have mu in the null and the alternative hypothesis. Okay, so we have mu there and mu here. We always have an equal to in the null hypothesis. The alternative hypothesis is based on what are we trying to prove, right? So Lexmark wants to prove that it is less than that. So we'll do a less than, right? And then the 1,062, that Canon's claim was, right? They said they should print an average of 1,062. So we're going to say, all right, we're going to assume that's true, that the mean is equal to 1,062, unless we can prove otherwise. And we're trying to prove that it's actually less than that. We got a mean number of pages printed of 1,041, which is less than 1,062, right? But we want to know, is it statistically less, right? Or is it just less due to sampling error, right? If we did another sample of 70 printers, could we maybe just get 1,080 and then we get 1,050? Is it something just due to sampling error, or is this something that's really unusual to happen? So what we're going to do for that, I'm going to get my calculator up here. I actually got the fancy version downloaded because Texas Instruments is allowing people to use it for free right now with all the craziness going on, so that's exciting. So I got to have a blue calculator. That just makes life even better, doesn't it? I think it just makes me like math even more to have this nice blue calculator. All right, so we're going to go stat and test. We're going to use the t-test because we're doing means. All right, and we have the actual stats, right? So these are the important numbers. The sample mean, here, let me scoot this over. We had the sample mean was 1,041, our standard deviation was 59, and our sample size was 70, right? So that's all the information we need. So the first thing we're putting in, it has mu sub 0. So it wants to know what we're assuming is true. Okay, so that's coming from the null. Then our mean is 1,041. That's what we got from our sample. The standard deviation is 59. And our sample size is 70. All right, and then down here, this is how the calculator figures out where the p-value is. So to calculate the p-value, it has to know, are we trying to find the area less than the value or greater than, or on both sides of the curve? And so for ours, we're going to do the less than, right? So you want to choose the one that'll make it look just like this. You want it to look like mu less than 1,062, right? So that's what this would be, mu less than that 1,062, okay? And then we're going to calculate it. All right, and so the first thing you should check is right up here at the top. That's what your alternative hypothesis should look like. Okay, so if you want to make sure that you chose the right sign, look at this first and make sure that looks correct. And so that does match mine here, right? Mu less than 162. All right, and so this gives me a t-statistic of negative 2.98 if I do 2 decimal places, right? So that's telling me we can use the t just like we use the z in most scenarios. This is telling me that my statistic falls almost 3 standard deviations from the mean, right? Which is pretty unusual, we know from the empirical rule. Now the p-value is right here, so this p is the p-value, 0.0020. So this has a less than 1% chance of happening, right? A 0.2% chance of happening. So is that unusual? Well, we would say yes. In almost every scenario, that would be a very unusual event. But for ours, we're comparing it to alpha, right? So if we go back up here, we see that alpha is 0.05. Okay, so for an alpha of 0.05, when I compare my p-value to that, 0.002 is definitely less than 0.05. So it means we do have a significant result, right? This was an unusual value. So we would say we're going to reject the null hypothesis, add an alpha of 0.05, and accept alternative. So if I'm writing that out in a sentence form, that means there is enough evidence to say the Canon cartridges print less than 1,062 pages. So basically we can accept what our alternative was, which is that the average number of pages was less than 1,062. Okay, and we are pretty certain about that because we got such a small p-value, right? It was a less than 1% chance that it could have happened by chance, that it was just due to sampling error. All right, so that's how we would do one for means. Now if we're doing one for proportions, we're looking at this color report. I think we've talked about this a few times in notes. 23% of cars in North America are white. We want to know if the percentage of white cars at Sky is any different from the national percentage. We take a random sample of 250 students and find that 68 students have white cars. Using an alpha of 0.05, is that enough evidence to say the proportion of students at Sky that own a white car is from the national proportion? Okay, so again, trying to decide if it's proportions or means. There's no standard deviation in here, right? It doesn't talk about means or averages really, but it does talk about percentages, right? Proportions. So this one is definitely going to be proportions. So our null hypothesis and our alternative will have p instead of mu, right? We'll have an equal to in the null, And we're going to use the 0.23 because that's what this 2019 study said. All right. So 23% is kind of what we're comparing to. Now we're going to use a not equal to here because it just says, is it different? So maybe going into the study, we didn't know if we would have a higher percentage of white cars or a lower percentage of white cars, right? So we're just going into it saying not equal to. So if it falls far to the right or far to the left, then we'll figure that out, right? So let me get my calculator up again. All right, so for this one, we're going to go to stat again and test. And let's go to one prop Z test, right? So number 5. All right, so P sub 0, that's our null hypothesis. Make sure you put it in as a proportion. So don't put in like 23. Make sure you put in 0.23. And then all we need for proportions is just X and N. So how many people had white cars? We had 68, right? And our sample size was 250 students. And then again, we want our alternative to say the proportion is not equal to that 0.23, right? So that's what it should look like. So let's calculate that. All right, again, I check this and make sure it looks the same. Proportion not equal to 0.23. The Z here is 1.58. So my statistic was just about 1.5 standard deviations above the mean, right? So we would say in most cases that's not going to be real unusual, especially if we're doing a two-tailed test. So the p-value is going to be 0.1146 if we do 4 decimal places. So there's about an 11% chance that this would happen, right? And so now compared to our alpha, we were wanting it to be 5% or less, right? But ours was 11%, which is greater than alpha. So we're going to fail to reject hypothesis at alpha equal 0.05, and that's all you have to say. So when you come to that conclusion, you're kind of still, the outcome's kind of still in the air, right? You're saying, well, we might have a different percentage of white cars, but we just didn't have enough evidence to show it, right? It's like one of those, like we saw down here, where they're statistically tied. It's like, well, the statistic, for one person was higher than somebody else, but it's not enough. It's not a big enough difference to say that one person really is in the lead, right? So that's what this one's telling us here, is there's not enough evidence to say there's a different proportion of white cars at Sky compared to the national average or national percentage. So if your p-value is greater than alpha, you fail to reject the null hypothesis. If the p-value is less than alpha, then you reject the null hypothesis and accept the alternative. And that's really the main thing in chapter 10. I mean, the setup for hypothesis testing, like understanding like why we're doing it and how it all kind of works, can be a little confusing. But when you really get down to working the problems, you're really just using one prop Z test and the T test. You're using that to get your statistic and also your p-value, right? And then you're using the p-value to compare to the alpha and make your conclusion. Okay, so a lot of the hard calculation part is done in the calculator. You just have to be able to set up your hypothesis and make the correct conclusion, right? So the middle stuff is all done in the calculator. But again, of course, there are formulas and stuff to do that, but I would just assume you're doing it in the calculator. But if you have any questions about doing it, actually by hand, we can talk about those too. All right. So that's it. That's really the end of chapter 10. I only did 2 examples there because for hypothesis testing, most of them are pretty much the same. So you just need to be able to figure out if it's means or proportions and then know how to do both of those in the calculator. All right. So I hope that maybe I'll see some of y'all next week in the Microsoft Teams meetings. But of course, you can always email me if you have any questions at angela.galloway@kctcs.edu. And of course, I'll respond back to you in that way. As far as the final exam and the rest of the exams and everything in my labs, you have until May 8th to complete those. The final you can only do one time, but you can do it at any time where you're ready to take it. You'll just do it at home, just like you've been doing the other. All right. So good luck as you finish up these last few assignments and as you take your final exam. And if you have any questions, just let me know. All right. Thanks.